Hello everyone, welcome to Network Coding Lecture. My name is Vũ Nguyễn. I'm currently working at ComNet to pursue the doctoral degree. Today I'm talking about Fulcrum network coding in more detail and some basic solutions to improve its performance. This lecture is coming after the lecture of Professor Physics, so I would recommend you to watch his lecture first to understand the fundamental of Fulcrum network coding as well as random linear network coding. Alright, let's get started. Here are the contents that we will figure out in this lecture. Firstly, I will shortly revise the Fulcrum encoding and decoding, and then introduce you the very interesting scheme is adaptive decoding for Fulcrum Codes. Finally, we will learn about DSEP Fulcrum and its recoding mechanism. Let's look at the picture to see how Fulcrum encoder and decoder operate. Firstly, Fulcrum encoding expands an original packet into n plus r coded packets by using equation 1. So in this example, we have 4 original packets and 2 expansion packets. So these 2 expansion packets are created based on the outer coding coefficient, which randomly selected from high finite field, such as 2 to the n in this example. These outer coded packets are treated as the new coded packet in inner encoding process. Inner coded packets are created also use equation 2, where lambda Lg here are randomly generated from binary finite field. Okay, let's figure out Fulcrum decoder. As you remember that the main advantage of Fulcrum codes is to support for heterogeneous devices. So a receiver, depends on its computing power, can exploit 3 types of decoder: inner, outer, and combined decoder, to recover the original package. However, you have to remember that inner decoder is using binary operation, so it needs to receive at least n plus r linearly independent packets to decode successfully a generation, as shown in the table here. On the other hand, outer and combined decoder needs only n linearly independent coded packets to decode a generation. And of course, if the number of coded packets received is less than n, so the receiver cannot recover the original package in that generation. Here is the performance of Fulcrum codes. That maybe you already saw this in previous lecture. I'd like to show you again the trade-off between decoding probability and computational complexity, or decoding throughput here. As you see the figure on the right, the decoding throughput of binary finite field, such as RNC network coding, GF2, and inner Fulcrum inner decoder is very good. But the decoding probability is very low compared to the high finite field, as shown in the figure on the left. The question is how to improve the throughput of Fulcrum codes or reduce the complexity while maintaining the high decoding probability. Next, I'm going to introduce you the solution to improve Fulcrum's performance. The first approach is using the adaptive decoding algorithm for Fulcrum codes. So let's figure out an example where a sender tries to transfer 8 inner coded packets from different generations G1, G2, G3 throughout the network with different losses, and receiver tries to recover 4 original packets in each generation. In original Fulcrum codes, the receiver should choose either inner or outer or combined decoder before decoding starts. It cannot be changed in the middle. So in this example, if receiver choose to decode with inner decoder, the complexity is very low, but the number of coded packets needed to recover the original package is higher than outer decoder. So it means that we have 4 original packets and 2 expansion packets. So in each generation, receiver have to receive at least 6 coded packets to recover a generation. However, if receiver choose to decode with outer decoder, so the number of coded packets needed to decode a generation is less than inner decoder, but the complexity is much higher than inner decoder. So we can see the trade-off between the number of transmission and complexity. Another problem is that when the loss in the channel changes and sending the feedback from receiver to sender is impractical in some specific scenario, such as broadcast communication. Therefore, some generation cannot recover the original packets due to lack of received coded packet, like generation G2 in inner decoder here. Our new decoding algorithm is designed to adaptively choose to decode with binary fusi or high fusi, depending on the number of received coded packets. As you can see the red line, the number of received coded packets are enough to decode with binary fusi in generation Z1. But adaptive decoder automatically switches to decode with higher fusi in generation Z2 because the channel environment already changed, and come back to decode with binary fusi in generation G3. With this adaptive decoding, we can achieve the best performance in terms of decoding probability and computation complexity. So it means that we can maintain a high decoding probability of high fusi and reduce the complexity with low fusi, exactly the binary fusi. Adaptive algorithm not only addresses the chance of loss in the channel, but also can deal with the linearly dependent problem. This algorithm solves that feature. Assume that the receiver tries to receive and decode the incoming coded packet by using Gaussian elimination in binary or decode with inner decoder. Unfortunately, there are 2 linearly dependent coded packets after eliminating this matrix. Therefore, we cannot recover this generation in binary fusi or inner decoder. In this example, we need at least 6 linearly independent packets to recover this generation in binary because we have n equal 4 and I equal 2. But the number of linearly independent coded packets here are 4. Thus are enough to decode with higher field size. So the algorithm will map back these linearly independent packets to outer code and operate with higher field size. And finally, we can recover the original coded packets. Here are the results that we have achieved. Delay here is defined as the number of additional coded packets transmitted from sender to receiver over the lost channel. The figure on the left shows the decoding probability for different delays over 20% of erasure probability, while the figure on the right shows the complexity in terms of number of operations. So we can see that the decoding probability of adaptive decoder maintains as high as outer decoder, while it reduces the complexity from 33% to 55%. Here are some advantages of adaptive decoder. Besides the advantages of original Fulcrum codes, the adaptive decoding provides some more benefits, such as with adaptive decoder, receivers adaptively decide to operate with low or high finite field, suitable for the chance of channels, reduce the complexity by up to 55%, increase the number of the decoding probability as high as outer or combined decoder. Let's move on to another scheme to improve performance of Fulcrum codes, that is DSEP Fulcrum. Remember that adaptive decoder is designed for only receivers. However, the encoding process impacts significantly on the whole communication system, including senders, intermediate nodes, and receiver. In this scheme, we will focus on dynamic sparsity and expansion packets for Fulcrum encoder and provide a good recoding mechanism. Okay, this is another figure to show the number of linearly dependent packets increase significantly at the end of the generation. For the lower field size, such as CF2 has high linearly dependency in the end of generation. However, with higher field size, such as CF2 has nearly no linearly dependency, but high complexity. The question is how to reduce the number of linearly dependency at the end of the generation in lower field size, and also reduce the complexity in higher field size. The solution is to adjust the sparsity level in encoding coefficient and reduce the attendance of expansion packets in coding coefficient. This shows in the coding coefficient matrix. So the way we generate the coding coefficient vector also affect too much the performance of encoder and decoder. So the common solution is that we try to generate a sparse non-zero coding coefficient at the beginning of generation, and also we increase the density of non-zero coefficient at the end the generation, and also we assign a lot of non-zero on the expansion coefficient, and then we increase the number of non-zero at the end, the coding coefficient. But the question is that where and when should we increase the number of non-zero coefficient. So this slide compare the conventional Fulcrum codes and DSEP Fulcrum in terms of sparsity and the way to generate inner coded package. For conventional Fulcrum codes, we use static sparsity. So it means that we assign the static sparsity before we generate the inner coding coefficient by using this equation. And in DSEP Fulcrum, we derive the function omega I to adjust the sparsity level based on a set of parameters such as n, r, omega, v. After generate the sparsity level, we use the sparsity level to generate the inner coding coefficient lambda, and with the specific number of non-zero coefficient generated by lambda, so we can create the inner coded package based on this equation. These figures show the change of sparsity level omega I for generation of 100 with different redundant package delta. So with different delta, we have different level of sparsity, and when the number of received coded packets increase, the sparsity level also increase. So we can see here the difference between two figures is the chance of consider expansion V. So the sparsity level in two figures here is the same. The left figure shows the chance of V in different regions. So it means that we divide the generation into different regions, and we will change V at the end of this region. On the other hand, another scheme, we also try to change width at the end of generation, because you remember that almost the number of linearly dependent packets happen at the end of generation. Here is the decoding property that we have achieved for different expansion packets and the number of additional coded packets received. For r equal 10, the decoding property of these SEP schemes is even higher than another SEC technology, Raptor Q. Here is encoding throughput of DSEP compared to Raptor Q. We can see DSEP achieved substantially higher encoding throughput than Raptor Q for small generation size. For example, for generation size of 16, DSEP is higher than Raptor Q 17 times. Even DSEP employs 10 expansion packets. And for high generation size, for example, n equal 512 or larger, RaptorQ achieves higher than DSEP, but RaptorQ performs systematic encoding while DSEP performs non-systematic. Here is decoding throughput of DSEP compared to RaptorQ. Similar to encoding throughput, DSEP decoder also achieves substantially higher than RaptorQ for small generation. For the case of yes equal n plus 20 here, RaptorQ achieves higher throughput but still lower than DSEP. However, in this case, RaptorQ has to send totally 36 coded packets for a generation of 16. It's too much, right? For the large generation, RaptorQ achieves much higher than DSEP, but with application employs this generation. So maybe you can find the answer. We also measure the energy consumption of DSEP in different Android devices. As we expected, DSEP also achieved low energy consumption compared to the other schemes such as RNC or original Fulcrum. So let's figure out recording mechanism of DSEP Fulcrum. As you know, the original Fulcrum codes use only the binary field sign as recoders to recombine the coded packets. However, the original recording mechanism is not suitable for DSEP because it tends to cumulatively increase the decoding density, therefore reduce the throughput at recorder. And it might create a linearly dependent coded packet and also faces the problem of limited memory at the intermediate nodes and also waste the resources if all the coded packets in a generation are stored at the intermediate nodes. We can easily to see this issue in this figure. The overhead here is defined as the ratio between number of linearly dependent packets and the original packets. The overhead is reduced much when we increase the queue size at recorder. The queue size at recorder here also means that the number of coded packets we will recombine, generally recombine together. But if the queue size is greater than 10 in original recoding, the overhead is not changed anymore. This means that if we store and combine more than 10 coded packets at recorder, it will be useless. For example, 20 or 24. Therefore, if we have a good recording mechanism, so we can avoid this issue. Here is the DSEP recording mechanism. It allows recorder to store a few coded packets in the buffer, and a new incoming coded packet is always combined with the rest one in the buffer. So let's see the buffer here. So if a new incoming coded packet is received at recorder, is stored in the buffer and also always combined with another coded packet in the buffer to make sure that the new coded packet appears in the new recorded packet and sent to the receiver. Here are some results of recoding mechanism of DSEP. The figure on the left shows the number of transmissions for different number of intermediate nodes. For DSEP recoding with only 3 recoding symbols, so it means that it uses only 3 coded packets on the buffer to recombine the new coded packet, can achieve really low number of transmissions. And the figures on the right show that the DSEP can achieve really high recording throughput, and because we just only store 3 coded packets on the buffer, so we also save a lot of memory at intermediate node, and it also maintains the low density level at encoder, and this leads to maintain the high decoding throughput at receiver. So this SEP mechanism provides simple operation at routers devices in the network.